Okay, so we're in chapter 7 now, and chapter 7 is primarily focused with techniques of integration. What we're looking at are ways of evaluating lots of different types of integrals. Up until this point, you've learned a very small set of techniques for evaluating integrals. Your main theorem, I guess, or your main method for evaluating integrals comes from the fundamental theorem of calculus, where we know that indefinite integrals, for example, can be evaluated by finding an antiderivative for whatever your integrand is. But that's easier said than done in a lot of cases. As you have now seen with the integrals that you've been exposed to, it can be very difficult sometimes to come up with an antiderivative for a given function. Much more difficult in a lot of cases than just finding a derivative. So chapter 7 is going to give us a much larger set of tools for doing exactly that. It's not the only thing we talk about in chapter 7. There's a little bit at the end where we deal with numerical integration, which is a little bit different, but we'll get there when we get there. So the first technique that we want to talk about today is something called integration by parts. And really what this is the counterpart to the product rule for derivatives. It's kind of like the integration version of that. And in fact, it actually comes from the product rule. So we're going to talk about that for a second. First of all, the types of integrals that we're looking at here, for the most part, when we want to use integration by parts, are integrals of functions that can be thought of as a product of two functions. Now, just because a function looks like a product of two functions does not automatically mean that integration by parts is the way to go. A lot of times, u substitution by itself is enough to solve that type of an integral. But in other cases, u substitution is not quite enough. So here's one example where integration by parts is going to be really helpful. The integral of x e to the x. I'll let you sit with that one for a second. Think about how you might go about solving that with the tools that you currently have. You'll probably figure out soon enough that just regular old u substitution does not quite cut it for this type of an integral. So we need something else to approach this with. So like I said, integration by parts is really dependent on the product rule for derivatives. So let's look at the product rule as a bit of review here. If you have two differentiable functions, f of x and g of x, how do you take the derivative of f times g? Well, we know from calculus 1, the product rule says that this is equal to the first function times the derivative of the second, so f times g prime, plus the second function times the derivative of the first, g times f prime. Okay. Oftentimes in calculus 1, we simplify this notation by, instead of using function notation, we assign variables to those functions. So if I were to let u equal f of x and v equal g of x, the product rule here can be written in a simpler form here, where instead of f of x, g of x in there, I just have uv, and then I'm taking the derivative. So uv prime is equal to uv prime plus vu prime. That's the same thing that this is saying, but in a simpler notation. Okay? Now, I'm going to move some things around in this equation here. Specifically, I'm going to subtract the vu prime from both sides, and then I'm going to switch which side each expression is showing up on. So I'm going to have uv prime isolated, but I'm going to put it over here. And then on this side, which is now this side, I'm going to have uv prime minus vu prime. Okay? Now, we're gonna recall something about differentials, which you also learn about in calculus 1. If I have u equals f of x, then I define the differential du to be f prime of x dx. And similarly, dv, given the way that we're defining v here, would be g prime of x dx. The reason I'm doing that is because I'm about to take an integral, an indefinite integral of both sides of this equation here, and I need those differentials to be showing up in there for the integrals to make sense. So if I were to integrate both sides, then uv prime, where v prime is the same thing as g prime of x, I can think of that as the integral of u dv. So notice my v prime becomes dv, which really means g prime of x dx, but I'm going to write it like this, simpler notation. If I take the indefinite integral of this side, notice this entire expression is the derivative of something. I'm taking the derivative of uv. And we know that indefinite integrals will undo that because that's the fundamental theorem of calculus. This is going to give me the antiderivative of that derivative, which essentially just cancels the derivative out, giving me uv. I just noticed I have a typo here. That should be a minus, like that. Sorry about that. Okay, once I've done that, I also have to take the indefinite integral of this side, which I'm going to write in this form, the integral of v du. This is actually what integration by parts is. So typically what you're doing is you have an integral that looks like a product of two functions, and you think of one of those functions as u and the other one as dv. And then from that, you can figure out what du is and what v is, and put them into where those things appear on this side. And then notice that that gives way to another integral that you have to deal with, but the idea in integration by parts is that this second integral is more manageable than the one that we started with. So let's actually look at an example to see what I'm talking about. Back to this integral that we dealt with in the first place. Okay, what I'm going to do is I'm going to take this product of functions and I'm going to try and think of one of them as a u and the other one as a dv, right? One of them is u, one of them is dv. So I'm going to say, let's let u equal x and let's let dv equal e to the x. And because I'm talking about this differential, I have to include that dx with it. So let's put that in there as well, ex dx, okay? Now, and I'll point out why I chose which one of these to be u and which one to be dv in a moment, because there is a strategy there, but let's work through it and it should kind of reveal itself. So to use integration by parts, I have to know what u, v, and du all are. So that all that stuff gets plugged into this side. So let's figure that out. If u is equal to x, what is du? It would just be dx. And if dv is e to the x, what is v? Well, remember, this expression, the e to the x here, is like the derivative of whatever belongs up here. So to get from here to here, I need to take an antiderivative. But the exponential function is its own antiderivative, so I get e to the x. Okay? Notice the order that I wrote these in, by the way. I put u here and then dv kind of diagonal to it. Not everybody does that. That's kind of my own convention that I like to do. And the reason I do that is because it keeps the u's sort of vertically aligned and it keeps the v's sort of vertically aligned. But that's not necessary. You just need to make sure you know what's what. Okay, so now if I want to evaluate this integral here, the integral of x e to the x dx, using integration by parts, the first expression I should be writing down is uv, which in this case looks like x e to the x. Okay, minus, so that was my typo before. I put an equals instead of a minus, but it should be a minus v du. V is e to the x, du is just dx. So this becomes e to the x dx. Now notice what happened here. When I did integration by parts, which is this technique, this integral on the right-hand side is now much easier to evaluate than the one that I started with. This just becomes x e to the x minus, and I know that that's e to the x. And then because this is an indefinite integral, I can't forget to put plus c. Remember, that's your constant of integration. Don't forget your plus c. That's it. That's the whole thing. So we have figured this out. And if you, as a reminder, if you're doing an indefinite integral and you want to see if you got your answer correct, how do you do that? You can check it by going backwards. We took an antiderivative to get here, so if you take a derivative of this function, it should take you back to your integrand. I'll let you do that, but it's a good idea, especially as you're getting used to these new techniques, to check your answer by differentiating first, okay? So that is the first example under our belt. So let's do another one. So for this one, I want to evaluate the indefinite integral of x squared cosine of x. And again, notice what we have here is a product of two functions. And again, just the fact that an integrand is a product of functions is not immediately telling you that you have to use integration by parts. Sometimes other techniques work. But aside from integration by parts, your main technique that you have is either knowing the antiderivative right away using, the fundamental theorem of calculus, or using U substitution. And you're going to find if you try either of those that it's not immediately obvious how to deal with this. So we're going to try integration by parts. Now, I want to actually return to my previous example here really quick. I did mention before that the U and the dV were chosen strategically. And I didn't really say what the strategy was there. So let's revisit this for a second. What was it about choosing U to be x and dV to be e to the x dx that made this work out so nicely? Well, it's the fact that I chose a polynomial, really a monomial more specifically, but a polynomial as my U term, because polynomials have a really nice property when it comes to derivatives. The powers on them get smaller as you take derivatives of them. That's the power rule. So this x shrunk down to a dx, which was a much more manageable thing to be showing up in this integral than the x was. So oftentimes, if we have a term, or a factor, I should say, in this product here, in our integrand, that looks like a polynomial, in many cases, it's best to let U be that thing. Okay, in which case dV now is going to be cosine of x dx. And again, why did I want U to be x squared? Because when I start taking derivatives of that, so du, I'm going to shrink that exponent down. 2x dx is what I get. I made this a little bit cramped. V here would be just sine of x. That's the integral, or the antiderivative. Okay, so now let's see if we can work this out. The integral of x squared cosine of x dx is equal to what? Well, integration by parts first has me taking u times v, so it's going to be x squared times sine of x minus the integral of v du. So that's 2x times sine of x, and then I'm going to put the dx from there at the very end, so that's 2x sine of x dx. Okay, so that's not bad. That's pretty nice. But what do we do from here? Well, the integral that I ended up with here, although the power on that x is smaller, it's still not quite at a point where I can solve it in a very straightforward way. So this is an example where you need to apply integration by parts more than once to get to an answer. Okay? So what I'm going to do is I'm going to take this integral here, and I'm going to choose a new u and a new dv. So this time, let's let u equal 2x, and let's let dv equal sine of x dx. So now du equals 2dx, v equals negative cosine of x, and that's what we're going to be using in our integration by parts. You got to be really careful with this next step. And here's the reason why. I have my first term here, nothing changes with that, x squared sine of x minus. As soon as you write this minus down, create a set of brackets or parentheses. And the reason that's really, really important is because this single integral is about to become two terms. Integration by parts produces two terms out of this one integral right here. And that minus sign needs to distribute over both of those terms. If I don't put these square brackets here, I am likely to forget to do that. So setting up my integration by parts now, uv is going to look like negative 2x cosine of x minus the integral of v du. Okay, so looking at that, I have a negative cosine of x and a positive 2x dx. When I multiply these, I'm going to get negative 2 cosine of x dx. The negative from that negative 2, I can go ahead and just bring out and make that a positive. Okay? So that leaves me with 2 cosine of x dx, just like that. All right? Now let's work through this. X squared sine of x. I have to distribute that minus in, so that's going to become plus 2x cosine of x. And this thing that I just changed from a minus to a plus is about to become a minus again, because that minus is going to distribute right into there. So that gives me minus, and then I can write the integral, or I can just evaluate that integral, because this one is easy to do directly. The antiderivative of cosine of x is sine of x. So really with that 2 there, I get 2 sine of x. And then as a final step, don't forget plus c. Okay? So that's it. There we go. So again, sometimes to do these problems, you need to apply integration by parts more than one time. And that's what we needed to do here. Okay? We have more examples to work through. Let's do that in part 2.